Hello, welcome to this video. Pretty much this video is pretty much going to talk about proving that a subset problem is in the set of NP. Um, so it's an NP hard reduction problem, and the video pertains to design and analysis of computer algorithms, CSC 705, and the instructor for the class is Dr. Austin O'Brien. So without wasting time, I'll just hop on to I prepare a slides for it, and I'll use the slides and some writings to show my presentation. So as I said, it's a subset problem. To show like a subset problem is NP complete. So when we talk about the subset problem, I'll first talk about the first NP. NP is a problem that is solvable in non-deterministic polynomial time. So that is a random time. We can guess the output of it. So a set of P is a subset of NP, which is the P problem solvable in polynomial time. A set of P is a problem solvable in polynomial time. So when we have an NP, we can have problems that are solved in polynomial time. NP don't stands for like non-polynomial time. Problems solved in non-deterministic polynomial time. And like we are like, it's pretty much making some guess and to check to see if you can solve it in polynomial time, like a yes or no. So at least if we have one problem that can be solved in polynomial time, then we classify that set as an NP. So, and the whole theory or the whole idea behind this presentation is proving like a subset sum is a set of when we have a set of non-zero natural numbers is an NP complete. Moving forward, so I'm just going to explain the subset a little bit, then we can proceed from there. So the subset sum is an NP, but it's not in the set of P. It is hard. It's a hard problem and can be solved in polynomial time. From the research and my understanding, input, if you have a set of S, which is W1, W2 to Wn of natural numbers, and the target is W, the problem should return 1 if and only if there is a subset S prime which belongs to S that adds up to precisely W. So when we, to explain it for a layman to understand, we have a set of natural numbers which is 3, 34, 4, 12, 5, and 2. If we are trying to look over and get a sum that equals to 9, we can get a sum which W is 9 in this case. The output is true. Why? Because there is 4 and 5 that have a sum of 9. So that is a classified clear example for just a lay person to comprehend what is going on. And when we talk about NP complete is if it is in the set of NP and every problem in NP reduces to it. So that is how or why it is going to be an NP. That the problem is in the set of NP and it is NP hard. So is in the set of NP and every problem in the set of NP can reduce to it. So before I proceed, I'll first try and show the subset problem is in the set of NP. Then, so I'll just escape from this side and show that proof. So that the subset is in the show that the subset is in the set of NP. So you use let's say which is like means subset that are make true. So proving that 3SAT is NP-complete. And the first one we're going to do is like 3SAT is in the set of NP pretty much because we can verify a solution in polynomial time. Here we have like x1, x2, x1, x2, x to left, intersect, where x1 is equal to 0, x1 equals to 1, and x2 equals to 1. So I'll continue from my slide and continue with the proof from there. So we show that you show that the subset is in the set of the NP. That is what I was to make the SAT mean satisfiable. So the theory is the theorem subset sum is NP complete. We can use a three-dimensional matching, which that is what we can then we reduce it from 3DM to SS, and we make our proof. So I'm just going to talk about a bipartite matching problem, where we will be given a bipartite graph of G of x union y to yield, and we wanted to find the maximum subset of the edges that do not share any endpoints. We say that a matching M is perfect if every vertex in x union y is covered by an edge in M, pretty much. And it is easy to see like G has a perfect matching. Then we have x equals to y, and the otherwise at least one vertex not match. So we can think of x and y as two sets of equal size of n. Then we can have T complement x times y be a set of pairs of the form xy, s1 and y1. So I'll continue with the 3D matching. So an input of three sets x, y, z of equal size n, and set T C complement of x, y, and z of triple x1, y1, and zz, such that si e into y1 and y implementing z, right? Then the problem, we should return 1 if and only if there is a subset of T complement in T, such that every element of x union y union z is in exactly one triple. So like this like generalized form of two sets x, y, generalizing the set of two sets x, y to three sets x, y, z. That is the whole idea. So we first show SS is NP, and we have to consider the instances of SS, and we have to encode the subset of S prime into which is the set of W1, W2 to Wn that is supposed to sum up to W in polynomial time, and we can compute the sum of these numbers by verifying if the sum does indeed equals to W. And the second is we show that SS is NP hard by giving a reduction from 3DM to SS. This means giving an instance of X, Y, Z, T of 3DM, we construct an instance of SS of set S SW such that SYZ has 3D perfect matching. If S has a subset that sums up to exactly W. So that is what we are going to use. So we are going to use the 3D matching. And we're gonna have like an input of 3 sets, right? Which is X, Y, and Z equals size N. And set T of X times Y and Z of triple let's come a new line x1 y1 and z1 such that x1 is x y1 e y and z1 e z. So like the problem is return 1 and only if there is a subset T raised to the power 1 such that every element of X U Y U is in exactly 1 triple. And we just do this like generalization from 2 sets, which is X, Y to complete it. As I mentioned before, X, Y, and Z. And you can accomplish this, this set through graph by using hypergraph. I wouldn't go much with the hypergraph. So firstly, you prove or show that SS is NP, and that is what like you can do that. Consider an instance like we consider an instance of SS, by encoding subset S raised to the power 1, which is equals to w1, w2, all the way to wn. That is sum up to w. So in polynomial, like, we can compute the sum of these numbers to verify the sum does indeed equals w. So then I think second, we show that SS is NP by giving a reduction from 3dm to giving a reduction to 3dm to like 3dm, then we reduce it to SS. This means as giving an instance x, y, z of 3dm. You can construct an instance of SS of S W has a 3D perfect matching S as subsets that sums exactly W. So we have like for each T in T where T is x1, y1, z1, we construct a correspondence number W2 with 3n digits, where we place a 1 in positions the ones in positions 1. Then n so for each for T, which is x1, y1, z1, base n plus 1. We find W to be n base n plus 1 with 3n biggest. Each of which is equal to 1. Yeah, and now we can claim that the set of triple T contains a perfect 3D matching. So we can claim that the set of triple T contains a perfect 3D matching if there exists a subset of the numbers. Remember the WT adds up to W. So first, suppose you have 3D matching that consists of triples T1, T2 up to Tn in the sum of W T1 plus WT2 up to WTN. There is a single 1 in each of the 3 n digits positioned by a construct. So the result is equals to W by construction of W also. So if you have like the 3 conclusion, 3D matching consists of triples T1, T2, T3 all the way to Tn. And the sum WT1, WT2, WT3 all the way to WTN. There is a single 1 in each of the 3 and the positions by constructs. So the result is equal to W. Yes. So go back to my slide. So we now claim that the set of triple T contains a perfect 3D matching. 3D matching if there exists a subset of numbers WT that adds up to exactly W. So I think that should be the last part of my slide. Thanks for watching. I do appreciate it. See you next time. Bye.